Hi, my name is Ruslan Partsay. I will present our work called Robust Visual Odometry for Realistic Point Goal Navigation that was done in collaboration with Olis Dubosavich and Alexander Maksimets. Our experiment setup follows the Habitat Challenge 2021 benchmark. An agent is spawned in an unseen environment and has to navigate to static point goal. No ground truth map and GPS plus compass sensor are available. The agent must only use its visual sensory input to navigate. We used a high-level architecture of the point goal navigation agent from Samyak and colleagues, but a two-layer LSTM-based network is used to approximate the navigation policy. The visual odometry module takes the pair of RGBD frames as input and predicts the relative pose change. Predicted pose change is then subtracted from the goal location, and the result is fed into policy as a new goal location. We train policy and odometry separately, and then replace the policy ground truth localization signal with odometry module estimates. We leverage the decentralized distributed proximal policy optimization algorithm to train the policy. We consider the navigation policy training setup introduced by Wiremans as the initial setup in our experiments. Following the work done by Zhao and colleagues, our odometry model is represented as a ResNet encoder with half of base planes following the compression block and fully connected layer with dropout. We use ResNet 50 and group normalization. We concatenate an action embedding to each fully connected layer. The model is trained using mean squared error regression laws for translation and rotation. We also downscale the observations twice during training and evaluation. In contrast to the related works in the field that use the odometry model and odometry module interchangeably, we consider the module a more high-level abstraction that can comprise one or more odometry models. In our case, we use a single model odometry module and increase the model robustness to noise by incorporating observation augmentations during train and test time. The visual odometry model is trained and evaluated on the generated static dataset consisting of pairs of observations navigation agent receives before and after taking a particular action. We apply the visual odometry dataset collection protocol similar to that used by Zhao and Samyak. We use a shortest path follower agent to unroll trajectories from which the pairs of RGBD frames with meta information about actions taken and ground truth ego motions are uniformly sampled. To the best of our knowledge, the dataset has the largest number of observations among all we studied in related works, with around 5 million observations. We enrich the training dataset diversity by randomly reflecting 50% of visual observations along x-axis during training. The same type of augmentation is also applied at test time, and the final ego motion is computed as the average ego motion between original observation frames and flipped frames reflected back. Our experiments show that by applying such augmentation, we may not only decrease the validation mean absolute error for relative post-regression given two consecutive RGBD frames, but also increase the agent robustness to noise further when used as test time augmentation during navigation. We also add inverse observations for rotations during training by swapping source and target frames. The same type of augmentation is applied at test time, and the final ego motion is computed as the average ego motion between original and swapped frames. It also serves as a regularization when turned on for navigation. Our navigation agent follows a near-perfect path for both episodes with a relatively small geodesic distance to target and episodes with a large geodesic distance to target, and can perform sophisticated backtracking where the wrong way was chosen. Our best performing agent is ranked number 2 on the PointNav test standard leaderboard with respect to SPL and success, and is number 1 with respect to distance to goal even without policy and odometry fine-tuning, just by replacing ground truth localization signal with odometry module estimates. Our agent performance matched the pretty close agent with ground truth localization on Gibson validation split and has the same distance to goal. We believe the 3 points of SPL and 4 points of success difference between the agent with perfect localization and agent equipped with our visual odometry module can be addressed with fuzzy policy and odometry fine-tuning, scaling, and hyperparameter tuning. Thus, effectively, GPS plus COM plus replacement problem is solved for this task. Many thanks to the Habitat Challenge organizers for pushing embodied AI research forward.